Everybody, it's time for us to get started, so let's do so. This is our second class meeting. We didn't take the first one, but this is our second class meeting. I'm glad to see everybody who's here. I want to take just a minute to kind of go through the roll and see who might be coming a little later, so this won't take a second. So Tiffany's here, Christy's here, Michelle is not taking the class. This must be something. Christy's here, Ashley's here, Allison's not here, Melissa's here, Angie's not here, Julie's here, Aaron's here. I think Nat and Dennis are on their way, and Jennifer's here, and Joanna's here. Okay, so we have a few people who probably will be coming in a little later, and a few people who might be at the other session. The next thing that I want to tell you is that I want to remind everybody, and Melissa reminded me just a little while ago, that at our next meeting, we will have test 1. And that is, I think, October 18th. Is that correct?
Yes.
Okay, that's what we have. And what I'm suspicious of is that we'll have what we did in Chapter 5 and Chapter 6 on this. We need to push a little faster to get through Chapter 6. I'll be putting up some videos this week that'll help us get through that. And I probably will do one more homework assignment. There will be a homework assignment. Number 2, homework 2, on integration before the test. This is Chapter 6. I'm not talking about right before the test. Before the test, enough time that I can grade it and get it back to you. Those solutions. So that's what we have on tap. We are in Chapter 6. There's 11 videos posted, which is not that many. We've had 6 weeks, but that's what we are. And what I want to do today is I primarily want to recover, if you will, some of the information on integration, maybe with a little bit more examples. So this is for Chapter 6. And that's kind of what I got in mind. But I also want to be available to answer any questions that you have, too. Maybe about, anything that's come up. But, when we run out of questions, I want to talk about the integration. Are there things that you want to ask about that we've done? It's okay to say no. Talk to us about integration, and I will.
I know our midterm isn't until October the 18th, and you were always really good about providing a study guide. How soon would you anticipate, or do you anticipate providing a study guide?
I'm going to give a study guide.
How soon?
Okay. So, Joanne, the answer. Well, I have a study.
By the end of today.
The answer is I have a study. I'm ready. But I was thinking I have one from last year. Okay. So, or the last time I taught it. The thing that I'm wondering about is how much of Chapter 6 we'll get through. And I won't put us in position. We're going to have a test that day. Okay, it's going to cover what we have comfortably covered up to that point. That's what's going to dictate what's on the test. I have a study guide that covers everything on for Chapters 5 and 6. So I can give you that study guide and then later say we're only going to do this much of it. Does that make sense? Mm-hmm. And I can provide that to you in the email tomorrow if you want. So the sooner the better.
The sooner the better. Just balancing everything and keeping the schedule straight and not the last minute rush, because that's also the end of our grading period.
Okay.
And that's sort of a selfish thing, but...
No, I don't think it's selfish. We want to put you in a position where it's the best for you to succeed. Okay, so I'll send out a study guide next time for the test, okay? Next time. It's tomorrow. Let's make it Monday. I don't go to school tomorrow. Okay? I just don't.
Monday's fine. Thank you.
Thank you. Okay, so I'll send it Monday. And then it'll be a study guide that covers what's on Chapter 5 and 6, and I might reduce the amount of material based on how far we get through.
Is that day I play tomorrow?
No, ma'am.
No, next Saturday, from what I understand from my husband, major game.
That's correct. That's a good thing. Not always a good thing, but a good thing. Alabama, usually Sundays are for pros teams, and Alabama usually pays their players. But we don't let people know that. And so, does anybody else want to ask anything structurally about the course, content about the course? What I got in mind is I'd like to cover some things about immigration. That's where we are. We haven't had a lot of information about it, but I'd like to talk. We're okay, Julie? You're saying go ahead.
Go ahead.
Okay, look, this has already been talked about in the videos. What I'm hopeful to do is to be here in front of you and to go over it with you and to drill home some points, even if I'm saying, what is this again? What is this again? So that we learn some material here. So what we talked about to start off with, in Chapter 6, we're talking about something called the Riemann Skills Center.
Dr. Whitaker,
Sir.
your camera.
Thank you very much. And anytime that I'm making that mistake, don't hesitate to let me know, and I thank you very much. I'm not going to thank you enough to pay you for it.
You know, an Alabama football player.
Ah. Okay, Riemann Stieltjes interval. And the first thing, ladies and gentlemen, the first thing is, we're talking about, in some sense, something that you've been exposed to in calculus. If we say the Riemann integral, that's what you're used to seeing. And the way we compute Riemann integrals is the fundamental theorem of calculus. And that's what we do. It's not the only way to calculate Riemann integral. There's other ways to define it, and such that you're taking some limit, and it can be kind of tedious, but for some problems you can still figure it out with this limit definition, okay? What we're doing in this class is we're going to first of all talk about the Riemann integral, okay? So we start off with the Riemann integral. Okay, now listen to me. The Riemann integral, we're going to say that's what we used to see. But how are we going to define it for this class? Here's the details for it. And then we're going to extend it to something a little bit more abstract called the Riemann-Stieltjes integral. The Riemann-Stieltjes integral actually encompasses the Riemann integral. Okay? There are certain situations where you're saying, this is the Riemann-Stieltjes integral, and what you write down is the same as the Riemann integral. Okay? So it's just a little bit more abstract. So what about the Riemann integral? So here's what we start off with. We start off with F, defined on A to B, into R, being bounded. That's what we're talking about. We're talking about a function. And it's defined on this range, and it's bounded. Okay? That's what we're talking about. And then, it's defined on this interval. So it's defined for every point on this interval. Doesn't mean it's continuous, but it's defined for every point on this interval. Okay, so it's being bounded. And then the second thing, we talk about a partition. So this is a partition of A to B. Okay? So that's what we're talking about. What is a partition of A to B? Where script P is, it looks like a set of numbers, x sub 0, and that's A. And then we have x sub 1, we got x sub 2, all the way up to x sub n. So there's, if you will, n plus 1 numbers. The last one is B, with xi being an element of A to B. So each one of the numbers I'm picking is in the domain of x. And x sub 0 is less than or equal to x sub 1, is less than or equal to x sub 2, is less than or equal to forever, all the way up to x sub n. Of course, this is B, and of course, this guy was A.
So a partition will always start with the first one in the integral and always end with the last one in the
Interval.
integral. I meant.
Yes, that's exactly right. And, I don't know, look, I'm trying to say things that are helpful. I don't know if you guys hear these things, but we talk about, you're in an office and you don't want to partition the room so you can have little bitty offices among you. And all they're doing is they're splitting up the room. That's all these things are doing. They're splitting up this interval into what we call subintervals. So let me give you an example. So if I look at, let's say the interval from, let's say from 1 to 9. Okay, I look at this interval. Then, script P, let's call piece of 1 equal to 1. So first thing, I'm going to list one thing. Thank you very much, John. I'm going to list one thing, Christy. One, the endpoint, the left endpoint. Then I'm going to have 3, then 5, then 6, 7, 9. That is a partition. Of 1 to 9. So essentially, when I'm looking at the x-axis, and I've got 1 here and I've got 9 here, what we're doing is we're saying, okay, we go from 1 to 3, we go from 3 to 5, we go from 5 to 6, from 6 to 7, and then from 7 to 9. So I'm breaking up 1 to 9 into 1, 2, 3, 4, 5 regions. That's what I'm doing. Is that okay? That's all we're talking about. And that's not the only partition possible, 1 to 9. There are infinitely many partitions from 1 to 9. And they don't have to have 1, 2, 3, 4, 5, 6 points. They could have 50 points. Okay? They could have 1,000,000 points. Okay? There's going to be a finite number of points, though, in our partition. Is that okay with everybody? That's what we're talking about. Okay, so this is a background thing for the Riemann integral. So we got these partitions. The next thing that we want to talk about with the Riemann integral is we're going to look at these subintervals, and we're going to say, we're going to let, this is C, m sub I, big M sub I, equal to, if you will, the supremum, or the maximum, of the f of x's, where x, that's what's changing here, is between x sub I minus 1 and x sub I. And I'm going to write right here, d, we're going to let little m sub I be equal to the infinity over all the x's between x sub I minus 1, I'm going to get out of the way, and x sub I.
What are your subscripts on the x's over there?
Yes, ma'am. It's x sub I minus 1 less than x sub I. And the same thing here. Now, Angie, let me give a really basic example so we understand what the heck we're talking about. Okay? I think it's not so, probably everybody understands and I'm doing things that are not so helpful, but I just want to give everybody a chance to look at it, to ask if they want to about anything.
And also, each partition has to have at least 2 elements in it then.
Every partition, every partition has to have at least 2 elements. Yes, the A and the B have to be. Yes, ma'am. Okay, so here, as a quick example, so as a quick example, if I let, let's do something really simple. So if I let f of x be equal to x, and let's look at it on from 1 to 9, and we have the same partition. So script P is going to be the one that we have, piece of 1 is equal to 1, 3, 5, 6, 7, and 9. And I've got this. So here's 1, maybe here's 9. Here's 1, here's 9. And then turns out that we go from 1 to 3, from 3 to 5, from 5 to 6, from 6 to 7, from 7 to 9. And if you look at this function, it looks like this. Y equal to x. It's this straight line. And I'm just looking at this right here. Okay. So what is big M sub 1? So I'm not going to do too many examples. We don't have that much room on the board, and plus once we do a few of them, it's just fine with that. M sub 1 is the soup of the alpha of x values when x is between x sub, well, it's 1, so here's 1 minus 1, and x sub, here it's just I, which is just 1 in this case. So if you will, this is x sub 0. Well, what's x sub 0? 1. It is. So this guy here is x sub 0, this is x sub 1, x sub 2, x sub 3, x sub 4, x sub 5. Okay, so this is really between 1, we're just looking over the interval between 1 and 3. And what we're trying to do is find the f of x values. Don't let me bother. I don't want to make things seem like it's true, okay? But I'm asking some basic questions. When I say f of x values, we're talking about x values or y values. Y. We're talking about output values. You're looking at the output values. Over this little region, where's the highest y value? Where's the highest output value? It's here. It's at 3. So this answer is 3. Is that okay? And then if I were to ask you, what's m sub, okay, let me pick one. Let's say m sub 4. So I'm skipping. I'm skipping some, Melissa. Aaron, I'm skipping some. What is this? This is the soup of all the output values as x runs from 3, or x sub 3 to x sub 4. That's another way of writing it. Instead of writing the x in between, I just put an interval. Joanna, that's all I'm doing. So Aaron, I'm looking at this thing. I'm looking at x sub 3. What's x sub 3? It's 6 up to 7. They say, what's the biggest value in between there for the output values? 7. That's the answer. Is that okay? And then, similarly, we can talk about the minimum values. We talk about the minimum values. And so, little m sub 1, for this particular example, what's it? It's the infimum, when we go from 1 to 3, of the f of x value. So I'm looking for the smallest value. I know the picture's over there. What's the smallest value, Melissa? 1. Okay? So it just turns out that that's what is the smallest value. This function that we're looking at here in this example is an increasing function. So its max and mins are going to occur at the endpoints. Is that okay? It doesn't have to be that way. I'm picking an easy problem out to look at. Okay? But I hope that gives you some idea. Is that okay? Of what goes on with this thing. So then, what do we define? We define something called the upper. So we can see DE. I think we're E. In making the Riemann integral, we define something called the upper sum. Upper Riemann sum. What is it? Here's what it is. It's symbolized by U, P, and F. Look, this is a function. It yields numbers. And what it depends on is the function you're talking about. So U is a function. Okay, it yields out numbers. What is it a function of? The partition and the function that we're talking about, the bounded function that we're looking at. And so what it's equal to is the sum, as I run from 1 to n, of m sub I times something called delta x sub I, which I'll just write down. It's what it is. It's x sub I minus x sub I minus 1. That delta, this is sometimes denoted, and we denote it by delta x sub I. That's the change in the x values. But if we can define an upper sum, we can define a lower sum. So lower sum. Lower Riemann sum, sorry. What is it? It's L with some partition in F, and it's equal to a sum, as I runs from 1 to n, of the little m sub I, x sub I minus x sub I minus 1. Okay, I can do examples, the one we're using, I can do the examples for the upper and lower sum for those. I'm going to. Okay? So here, we're looking at the same example. Oh, I erased the partition. I didn't need to do that. The partition was 1, 3, what was next? 5, 6, 7, and 9. Okay. So look here on the side, I'm going to kind of draw it small. 1, 3, 5, 6, 7, 9. And here's our function. It starts at 1, goes up to 9 in this region. And if I look at the upper sum with this partition in F, it's the sum as I run from 1 to, well, I run from 1 to n. What's n? So this is 0, this is 1, 2, 3, 4, 5, up to 5. Okay. Is that okay with everybody? I'm going to do it a little slower. This is x of 0, x of 1, x of 2, x of 3, x of 4, x of 5. I'm not talking about that. I want to make sure we get the details for something. Okay, what's this guy defined to be? It's defined to be the maximum value over each one of these subintervals times the delta x of I, or x of I minus x of I minus 1. Now look, what this is nothing more than the change in x between consecutive partition values. Change in consecutive partition values. That's what it is. Is that okay? Okay, so here, what are my numbers? Well, let me get a little bit more space. M sub 1. Well, on this interval, right here, what's the highest value that occurred? Well, it's 3. So it's 3 times 2. This distance. Just what's this minus this? 2. And then here, this is going to be 5 plus 5. So over this subinterval, 5 is the highest value, times its distance between consecutive partition points, which is 2, plus over this interval, from 5 to 6, the highest output value is 6, and the distance is 1, again 7, 1, and then 9 times 2. And that's the upper sum. That's a number. You just spit it out, okay? I'll find out more. I know this is part of it, and I just want to make sure that we're able to understand what's going on. And the lower sum is very similar, and I'm just going to write it down. It's going to be 1 times 2 plus 3 times 2 plus, it's 5 times 1 plus 6 times 1 plus 7 times 1. That's what it is. 2, that's right. That's what it is. And I was just taking the minimum values over each one of those. Is that okay? A lot of times when people teach calculus, they say, hey, look, we got the upper sum. So what we'd be doing for the upper sum is making rectangles that'd be hitting here. And we're talking about adding up all the areas of those rectangles. Is that okay? That's what we're talking about. You may have seen that before. That's what we're talking about. That's the upper sum. Nothing more than that. Okay? All right. Lower sums where we have smaller rectangles involved. The smallest possible. Okay. That's what we got. All right, well, good. Well, we haven't got to the Riemann integral. We're just getting background. And so the next thing we talk about is something called the upper Riemann integral and the lower Riemann integral. So here's the upper Riemann integral.
G.
Okay. So the upper
Yeah, that's right.
Riemann integral is symbolized for this type of problem. It's from A to B. We've got a little bar above the integral. Actually, we are.
Yeah. I just never had seen that
I
before.
hadn't either.
What?
The bar. I've never seen that.
That's what I'm putting down in the board.
No. I mean before your lectures.
Okay.
Yeah,
The
I hadn't
videos.
either.
Yeah.
But
At first I thought it was a mistake, couldn't find it.
Yeah.
it just means upper.
Yeah.
Above.
I figured that.
Good. I'm sorry, I'm just explaining how we do that. F and then dx. And what it's equal to, it's kind of funny, it's the infimum over all possible partitions of A to B of these upper sums. That's what it is. It's the in theme. Okay?
Is that something that you see in a calculus class usually?
No, not generally. No.
Okay, so that's why I've never seen it. Is that?
Melissa, you were going to say something?
Okay.
No, that's not.
I have a question.
Yeah, yes, ma'am.
When you say it's the infima over all the partitions of the upper,
Sums, yes, with partitions, yes.
you're assuming that, I mean, in our example, we only have one partition.
That's
Here,
exactly right.
We have a bunch of partitions and then we.
There are a
combine
bunch
the
of
other-
partitions.
Okay.
Yes, but we only look at
Because I was
one.
trying to relate that to the example and I thought, well, I
Well,
can't do that because we only have one partition.
You
So
can.
you only have one number.
That's right. That's exactly right. So there's infinitely many partitions that can be made of 1 to 9. And out of all those partitions possible, look at what the upper sum would be. Well, I mean, that's something to calculate. We're not really doing that. Okay? The only times that we can do that easily, the times that we can, is when we're talking about a constant function. Because it turns out that the big M is going to be the same every time. So it's not so hard to calculate. Okay? Okay, so wait just a second. You know, I wasn't sure about that. If you'll allow me, I would like to explore. So I just want to explore. So let's see what it does for this particular problem. I make it to a point and I say, look, this is not very beneficial. But that's what we are. How we doing today, man?
I saved us some seats, I appreciate that.
He's up here, right in front.
Good to see you, gentlemen. We've just been talking about introductory integration, okay, with some examples. That's what we've done. Okay, so here's what I'm going to tell you. I haven't explored this at all. I want to explore it in front of you. Let's see what happens. And if it isn't something easy to calculate, that is something also to note. That it's just hard to calculate, so we need some other way of calculating it, okay? So for our example, I'm exploring for our example. Okay, here's what I would be thinking. Notice every upper sum, so let P be a partition. I'm not saying what it is, except that, let me make it as general as possible. Let's say P is equal to X naught, which we know to be.
1.
Yeah, that's right. That's right. It's A or 1. That's right. So 1 is X naught, which is less than or equal to X1, which is less than or equal to X2, which is less than or equal to, all the way up to less than or equal to Xn, which is equal to B, which in this case is 9 in our example. Okay. Then what about the upper sum every time? Well, it has a certain form. Okay, because this is an increasing function, okay, the one we're looking at, the upper sum the maximum value always happens at the right endpoint. Is that okay? So I'm just following what we go. So this would be a sum as I run from 1 to n of, here this is x, it would be x of I times x of I minus x of I minus 1. Minus 1 index. Is that okay with everybody? That's what we'll do. That's the upper sum. Well, let's see what we get here. Maybe some things cancel. Maybe we'll get something. I don't know. Let's follow our noses. Erase the problem anyway. So here, this would be equal to the sum as I runs from 1 to n of x of I squared minus x of I times x of I minus 1. Okay. This would be a sum of I running from 1 to n of x of I squared minus the sum as I runs from 1 to n of x of I times x of I minus 1. I'm going to expand these just to see if I can get a feel for it. And if I say, hey, look, it doesn't seem to be yielding anything profitable, I'm going to say, okay, so you see it's hard to compute. Does that make sense? So here, this is going to be x of 1 squared plus x of 2 squared plus all the way up to plus x of n squared. That's what that is. And then this is going to be minus, so it's x of 1 times x of 0, plus x of 2 times x of 1, plus all the way up to, it would be the last thing, is x of n times x of n minus 1. Okay? When I look at that, I think, I don't see anything immediately that jumps out what it should be. Okay? I don't see what it should be. Seems like finding the soup of this expression. Seems difficult. It's not so clear. Is that okay with everybody? I don't see anything immediately about it. Is that all right? Okay. So we probably need some other way to find this quantity. Is that okay? And that's where the fundamental theorem of calculus may come in to help us. Okay, so these aren't easy things to compute. We did an example in the lectures of where I had a constant, and it was easy to compute there. Is that okay? But just this particular part doesn't look easy to me at all. Okay? That's what I'm going to write. Okay? That's where I'm going to leave. Didn't seem profitable, Angie. I don't think we're going to get anywhere. So. Okay, but that gives you some idea of what we're trying to do. All over, all partitions. That's what Christy, made emphasis about. So it's hard to get all the partitions. Okay? Okay. That's the upper Riemann integral. Well, what about the lower Riemann integral? The lower Riemann integral, it looks like this, a little bar underneath, a to b of f dx, and it's equal to the supremum of over all the partitions of these lower sums, which is also hard to compute. For most functions. Also very hard to compute. Is that okay? So we're thinking, okay, so we got these things, but only kind of in nice situations can we compute what they are, maybe. So, okay, not so easy to work with. We're not going to be working with it so clearly. I. The next thing we say, even though we can't work with them so much, we have a definition about what a Riemann integral is. Okay? It's the Riemann integral, we say when the upper Riemann integral equals to the lower Riemann integral, Then we define the Riemann integral to equal to it. Let's say the lower one, which is the same thing as the upper one. Okay? So we're saying, hey, it's kind of hard to compute these things, but when they're equal to each other, that's what we're going to define to be the total integral. Oh my gosh, that doesn't sound like too dang good of a definition. Maybe in theory it's a good definition, but it's hard to compute something. Is that okay with everybody? Hard to compute something. At least from what we know at this point of the introduction. Hard to compute something. Is that okay what I said? So we're going to have some other way. We don't even know when they're equal to each other because they're dang hard to compute. Let me do a bar above it. They're dang hard to compute. So when are they even equal to each other? I mean, how do we even know that? Does that make sense? So those are the types of questions that we're trying to work towards in this beginning part of chapter 6. That's what we're trying to do. And in trying to answer some of these things, the first thing that I want to tell you is, is this. Note, where? I'm not on the screen. If you look at the set of, if you let, I say it this way, let P be a partition. It doesn't matter what partition we're talking about. A to B. Then, if you take the minimum value, since f of x is bounded on A to B, there exists little m and big M such that for all x in A to B, M is less than or equal to f of x, which is less than or equal to big M, little m, big M. That's what it means to be bounded. The output values are between two numbers. There's two fixed numbers that bound all the output values. So, for any partition, what we have is, if you take this smallest value for f of x, if you will, over the whole A to B, and multiply it by A or B minus A over that region, that is going to be less than or equal to the lower sum of this partition in F. Which is less than or equal to the upper sum for that partition in F. And that's going to be less than the biggest value F takes on, or some other boundary values, times B minus A. I want to illustrate this with just a picture. Let's see what we're talking about. Okay, so, I got this. It doesn't have to be this function, but I'm going to draw the same function, like that. That's what I'm drawing. All right, I'm splitting it up. Here's A, here's B, here's my partition. That's my partition. What we're saying is that, look, if you take this value, I'm going to have to draw this picture lots of times. If you take this value right here, that's that y value, and multiply it by b minus a, that distance. It's kind of the area of that rectangle. Is that okay? the area of that rectangle is going to be less than or equal to the area of these rectangles added together. Which is the lower sum for this partition. Is that okay? Maybe I should be drawing another picture. You want me to draw two pictures to compare? I'll draw two pictures. Okay. Look, I draw it kind of small here. This guy was this. I'm splitting it up. Okay? I'm just splitting it up that way. Okay. So if I look at this, that's that guy. There, that guy. Okay? If I look at this, what is this? Look, if I could draw the exact same picture, you know, I'd be a counterfeiter if I was that good at it. So we're not going to expect this to be perfect. Okay? All right, what is this lower one? This lower one is, over this region, it's the same. But then it jumps up to here. Is that okay? And then it jumps up to here. It's this area. And can you see that this area is definitely going to be bigger than that area? And then this one, so this is just a kind of description of it, okay? Here, A, B, I'm still going to have the same marks here. The upper one is going to be, from here, it's going to be this. So take a look at that picture. It's going to be bigger than that guy. And then this one is this picture. But its area is this one. And it's the biggest of all. I'm drawing all this only for one thing, is to show this. This worked for any partition that we had, any fixed partition. Okay, we have one. And so what this is if you look at the set of all lower partitions, it's bound between these two numbers. So it's bound. So that means that for the lower sum, since it's a bounded set of numbers, the supremum exists. And so I can define the lower integral. Is that okay? I can define it at least. Even if it's hard to compute, I can define it. And because for the upper sums, that they're bounded between these two numbers here, because it's a collection, non-empty collection of non-empty subset of real numbers that's bounded in particular below, its infimum is going to exist. And so I can define the upper Riemann integral the way that we're defining it. Is that okay? It exists. It's some number out there. It may be hard to compute, but it's something. Is that okay? So that's what we can at least define it. Well, again, we're having, I'm not saying I'm talking about mathematicians. We're having a struggle to say, well, we got these things defined, but we're kind of having an abstract setting. How do we compute something? Does that make sense? Well, the first question to answer is, how can we even tell when these two things, upper and lower sums, are going to be equal? How can we even tell that? And so we work until we get to a big theorem. Okay? Big theorem. And let me do kind of a preliminary theorem maybe before that.
Can I ask you a question?
Yes.
So when the second picture and the third picture are the same, it's a Riemann integral.
Well, this is a picture for this particular partition. And so I can't draw every picture for each partition.
Yeah, but what I'm asking, I guess, is that your Riemann integral is when the lower...
The lower equals to the upper.
Yeah.
That means I'd have to be taking the supremum all over these equal to the infimum over all of these. I can't. There's lots of different pictures I have to draw
No, I get
because of the partitions. Okay. So I can't draw a picture and say, hey, they're equal, so there it is.
Right.
I can't do it. Okay. So what I want to talk about next is a big theorem, just to say when they will exist. But kind of working up to that, there's a few definitions I want to talk about. There's a big theorem we want to get to. So I hope the question is clear. When are these things going to be equal? When's it going to happen? Okay. Some space. Okay, so first of all, we introduced something called a refinement. Of a partition.
This should be J.
Group P is denoted P star. Or with. There's only one thing it has to have, with only one quality. Here it is that P is a subset of P star. Is that okay? Okay. Okay. So, here, if I look from A to B, here's my partition. This is script P. Then P star, I'm going to make the same marks as what I had before. Okay, that's P, but I'm going to add something else. As long as I add one more thing, at least one more thing, it is a refiner. I could add more than one thing. But the only thing I'm going to add are finitely many more things. Is that okay with everybody? Okay. So that's a refinement. Okay? And it turns out that when you look at refinements, they're going to have some kind of relationship between the lower sums and upper sums of a regular part, or the original partition. Okay? All right, before I get to that, let me say that there's nothing wrong with what I've said. Those are good things. But the name of this section is the Riemann-Stieltjes integral. Right now we've been talking about the Riemann integral. Okay? So there's a step of abstraction that's made. And here's what we do. Don't forget about it. It's fine. I guess before I move to this step of abstraction, let me write down one more thing. Okay. That is, given two partitions, P1 and P2, their common refinement is, and I'm just going to write it here. This is in the notes. It's P star equal to P1 union P2. So you just group them together. They got all points from each one of them. I was just looking to see if there was any colored chalk. I don't think there is. If there was, I could do two different refinements and show you. But anyway, you just group them together. So if it's marked, the refinement, the common refinement is a mark, takes every mark from each one of them and puts it on. So that's great. We got that about partitions. So here it is. L. We now extend the previous construction for, I won't call it L. Yeah, I call it L. For Riemann integration to Riemann-Stieltjes integration where F goes from A to B into R is bounded, and alpha goes from A to B, alpha goes from A to B into R is monotonically increasing. Yeah. And so I'm going to write these things down. Okay? So I'm quickly going to write these things down. And what I'm going to ask you, so this is the question for you to prepare yourself for. I said that this is a level of abstraction, but it encompasses the Riemann integral. So this is called the Riemann integral, or Riemann-Stieltjes integral. But whatever we say about this also works for the Riemann integral. The Riemann integral is a specific form of this guy. So that's going to be my question to you. When is it the specific form? And it has to do with alpha. Okay? I'm not looking for you to answer it yet, but we're going to recap here what we've done in the lecture. I'm just going to ask you, what's alpha to get the Riemann? Okay? I'm going to ask that to you in just a little while. Has anybody got any questions about what I've been talking about? So these are just definitions we're given primarily. Okay. So here, it's okay to ask anything you want to. So what do we do? Here's what we do. We say we have the big M sub I and little m sub I are defined as previously defined. Okay? That is that big M sub I, what's that equal to? It's equal to the supremum of the f of x's as x over, or in the interval from x sub I minus 1 to x sub I. Is that okay? And what was the little m sub I? Yes, infinity. Over all x's in, again, this closed interval, come on. X sub I minus 1 up to x sub I. The output value. Same thing, what we had. It's the smallest output value over these sub-intervals. That's all we're talking about. N. We've got the upper Riemann-Stieltjes sum. Here's what it looks like. Script U. It's the partition that's given to us, the function that's involved, and the alpha that we know to be an increasing function. Okay, those three things. And what it's equal to the sum as I run from one to n. Those are telling me how many partition points I have for script D. Okay? Then it's big M sub I, the biggest thing. And then you multiply that by alpha x sub I minus alpha acting on x sub I minus 1. No, sir, but you're close. That isn't quite right. So what Aaron was asking about or stating is what is alpha so that we get the Riemann sum, the upper Riemann sum. And you can say it right now. Okay? No?
F of I.
So alpha is equal to So, we're talking about a function. Alpha's a function. It needs to be an increasing function.
You look at identity function,
What is that? That's right. What is the identity function?
that's basically that.
That's right. That's what it is. If you I'll write it down. Note when alpha of x equals to x, this the Riemann-Stieltjes sum equals to the Riemann sum. Why? What would alpha of x of I be? It'd just be x of I minus x of I minus 1. And that is the Riemann integral, the upper sum. Is that okay? So we're just, here we're kind of extending the definition of the Riemann sum by saying we got any function acting on those partition points. We're talking about the differences of those. Is that okay? That's what's being done. That's the level of abstraction. But one of those alphas is alpha of x equal to x. And when you have that, you're talking about the Riemann integral. So Riemann integral, or Riemann integral theory, its theory falls under the theory of the Riemann-Stieltjes theory. Okay? Just where alpha of x is equal to x. So that's what I want to say. Let's get a few more things. Okay. So if I got the upper sum, I ought to have a lower sum. Thank you.
You're welcome.
It's equal to the sum I runs from 1 to n of the little n sub I. And here it would be alpha x sub I minus alpha x sub I minus 1. We got this guy, so here's the Riemann Stieltjes upper integral. Okay. What's it? It's this guy. From A to B, upper, put a little bar over it. F D alpha. Okay. What's it equal to? It's equal to the thema over all possible partitions of the upper. And then we got the lower. Yes. Get through the alphabet, then I start putting indices on them.
I thought we were done.
Hang in there. This is supposed to be helpful. Look, if it's not helpful, I'm doing something wrong because you're driving a heck of a long way. We'd rather be doing something helpful if you're saying, no, it's not. Do something else. I will. Okay, but hang in there. I think there's something important. This is reminding us what this is. We can't talk about these. We're in trouble because this is a theory. Okay? Okay, so that's what we're talking about. What's this guy? This guy looks like this. A to B. Got a lower bar here, F D alpha. And it's equal to the supremum. All partitions of these lower. Now, everybody, you might remember I asked for Riemann. I asked myself, and I answered the question. I said for Riemann, upper integrals and lower integrals, how do we know that they even exist? I said they're going to exist every time. How do we know? It's because we have bounded for the sets of the Riemann, upper Riemann sums and the lower Riemann sums. What was the bounds on those things? It was the minimum value for F all over times A, times, it wasn't A, it was Yeah, what was the change, right? Say it for me.
X of
Wouldn't that change? You look, that's right.
Ask your question again.
Okay, so my question was, what bounded the set, if you looked at the whole set over all partitions possible, for the, let's say, the lower Riemann sums? B minus, it was little m times B minus A, and what was bigger than it? The capital M, the maximum. Okay, is that okay? Well, what about these guys? What about this? If I look at the set over all possible partitions for this Riemann-Stieltjes upper sum, or Riemann-Stieltjes lower sum, what's going to bound it?
Would be alpha of M.
It's not alpha of M. So here's what bounds it. Here's what bounds it. So I want everybody not to be bothered. We're not saying we have to answer the question on the spot. It's that type of question, though, that is, it would be nice if that's running through your head. I mean, if this is something analogous to what we did in the Riemann case, what is it what we're doing here in the Riemann-Stieltjes case? Does that make sense? You know, we're playing kind of the same game. What's going on here? And what it turns out to be, even though I can't draw a picture for this, I can't draw a picture for this. So note, the little m, down in Sabah, the little m, it's alpha of B minus alpha of A. It's going to be less than or equal to lower. Partitions F, alpha, upper, which is less than or equal to big M.
Alpha B minus alpha A.
That's right, thank you. I'll write down something wrong. That's right. That's what it is. Is that okay? You know, I want to explain. So here, let us look at this part. Here's how I want to explain it. What is this? This is the sum as I runs from 1 to n of little m sub I. Okay? And then this is alpha of x sub I minus alpha of x sub I minus 1. Okay? Where this is the smallest output value over this interval. Forget the alphas, just over this sub-interval. And we'll break up A to B. Okay? That's what it is. Well, look at this thing. Here's what I'm going to tell you. This sum is the same thing as m. Little m is the smallest thing f ever. You think of it that way. Smallest thing f ever takes on. Okay? Well, maybe we don't even think of that. Maybe it's a little bit even. Smallest thing. Okay, that's it. And then here, I running from 1 to n. And then I'm still going to write down alpha x sub I minus alpha minus alpha x sub I minus 1. Now look, this is a constant, so what can I do with it? Alright, so that's right now. So this part right here, I'm thinking this is the same thing as this guy. Okay. Well wait, when I just do this quantity here, and if I were to expand that, what ends up being left, so think about this, m times, what's the first guy? It's alpha x sub 1 minus alpha x sub 0. And then it's going to be plus.
It's like your A and your B. Your x sub 0
Is A.
is A,
And your next one will have an
and
addition.
then, yeah.
That part's right, Aaron. I'm going to have alpha x sub 2 minus alpha x sub 1.
So it's like your alpha x sub 0 and alpha x sub n is going to be what's left over.
That's exactly right. That is right. That's right. So this is an m. That's what that was supposed to be. And this is what was said correctly by Ashley, is that everything, this term right here, see this guy right here? it's right here too. And they're free to be combined. And one of them's plus and one of them's minus. They're going to kill each other. They're going to eliminate each other. Okay? And so this ends up being alpha x of n. It's the only thing that lives minus, the only other thing that lives is x of 0. But as was said, so Aaron said they canceled out too. But this is equal to m times alpha of b minus alpha of a. And that's what it is. And that's why I wrote this part right there. That's what that is. But look, I wanted to, so this part is this, but really I want to look at it backwards. I want to look at it as this. So I'm thinking this part here, Dennis, is the same thing as this. Okay, that's what I'm thinking. These are the same. Let's look at it in this way. So this guy I'm looking at it this way. Look, these two guys, they're the same each time in each sum. Dennis, when I'm comparing these two guys, they're the same each time in each sum. What's different is this m compared to this m sub I. What's this m sub I? What that m sub I is the smallest f of x value on the subinterval. What's m? It's the smallest f of x value over a to b. So that one, that's right. That's right, Nat. So the m has got to be less than or equal to each m sub I. Is that okay? Okay, that's what we got. Is that okay? So that's what we're thinking about.
Which would be less than the capital and supplies.
Yeah, that's right. So that's all I'm going to say about it. Is that okay? Okay, there we go. Okay. Here's what I'm going to ask you. Does it matter if the m and m sub I are negative? No. Doesn't matter. Is that okay? Because what we're multiplying it by is, so m is going to be less than or equal to m sub I. That's for sure. Is that okay? Positive, negative, doesn't matter. What are we multiplying each one of those quantities by? Some differences in alphas. What do we know about the alphas? They're increasing. That's right. Good for you, Angie. They're increasing. So when you're increasing, this input value, I'm looking at x sub I minus 1. The input value is less than this input value. What do increasing functions do? They take smaller numbers, they take bigger numbers to bigger numbers. Is that okay? And so that means that this quantity is always positive, or it could be equal to 0. We said monotonically increasing, and for monotonically increasing, all you have to have is greater than or equal to. So it could be equal to. Okay? Is that okay with everybody? Okay, so that's what we got. All right. So anyway, and this guy, Aaron said the right thing, or somebody said the right thing. It's going to be less than this. I'm not going to go through the details of it. Okay? It's going to be less than that. Is that okay with everybody? That's the thinking. I'm just writing this on the board real quick when I'm doing a lecture, but that's the thinking behind it. So that means this is true for any partition. So if you look at all the sets of all the lower sums, they're going to be bounded between these two numbers, and so that means it's bounded. And so in this case, we're looking for the supremum. So the supremum exists of this sets, and if the supremum exists, we can define the lower Riemann sum. Is that okay with everybody? That's what we got. All right, great. Well, I want to look at some stuff that we have done. This is back. So, give me 1 second. Oh, wait a minute, I forgot the main thing. So I haven't defined what the Riemann-Stieltjes integral is, but it's going to be analogous to what we've said for the Riemann integral. How's it going to be analogous? That's right, and that's what we've seen in the notes. I forgot where I am. I think I've done P.
R.
I did Q?
Yeah. Yes. Yep.
So here we say F is an element of Riemann integrable functions with respect to alpha on A to B. Okay. If, so the lower
Riemann-Stieltjes integral of f d alpha equals to the upper Riemann-Stieltjes integral d alpha. Okay? And in this case, we say the Riemann-Stieltjes integral is, so here it is, it's from A to B, f d alpha. It's equal to the lower integral, which is the same thing as the upper Riemann-Stieltjes integral. That's what it is. But calculating those things are darn hard, except in very few specific cases. And again, how do we even know when these two things are equal? So, I mean, that's kind of tough, because calculating one of them is very hard, except for a few cases. Okay? So we build up some theory that helps us be able to maybe not calculate them originally, but just to know when they're equal. Is that okay with everybody? Just to know when they're equal. To say, hey, it's Riemann-Stieltjes integral, even if we don't know what the answer is yet. At least we know it's out there. Okay, so here's some things that I want to talk about, and that is some facts, some theorems. So we've had this idea of refinement, common refinement. I want to talk about involving that with Riemann-Stieltjes sums. So here's a fact. It says theorem. It says if P star is a refinement of P, and that's a partition. Then, here, the lower Riemann-Stieltjes sum with PF and alpha is less than or equal to the lower Riemann-Stieltjes sum with P star, the refinement, F and alpha. And the upper Riemann-Stieltjes sum with P star, F and alpha, is less than or equal to the upper Riemann-Stieltjes sum with P, F and alpha. Okay. And so Joanna, before class got started, said, can you see me after class because you said something in the notes where we're going to leave that to the students. And I want to make sure I can do it. Well, that's a good thing to make sure you're going to be able to do it, because earlier today, when we started, I said, we're going to have our test in 3 weeks. I'm going to give you a study. I'm going to give you a study guide tomorrow, not Monday. Okay, Monday I'm going to send it to you. But sometime in the next week or so, I'm going to send you a homework assignment. A homework assignment. Sometime in 3 weeks. And something like that. And one problem on the homework assignment is going to be to do the analogous proof, the proof of this part.
Does he agree with that?
Right here?
Yeah.
I've written what I wanted to. Okay? So I'm going to ask you to prove that part. Okay? Yeah, it's so funny. The refinement, wait a minute, the refinement's got more points. Is that okay? And the refinement's got more points. And so what happens is the lower sums get bigger when you get more points. Okay? So the more points you get, the more you get closer to its Riemann-Stieltjes lower integral. Because what is that defined? The Riemann-Stieltjes lower integral. What's it defined?
For all partitions.
What is it? The what over all partitions?
It's the supreme.
That's right. I'm going to tell you, for me, I'm a person. I have to think about that for a second. What was the definition? It's kind of opposite. This is the way I remember it, actually. Jennifer, this is the way I remember it. We talk about lower sums when we talk about their suprema. When we talk about the upper sum, we talk about their, and that's the way I remember it. Okay, now it's kind of backwards. We talk about uppers, we think, supremums are those. No, we're talking about their infimums. Okay? So this guy, the more points we get, seems like he's going towards the supremum. Is that okay, Tiffany?
Right.
And this one is saying, so Angie, the more points we get, the more this guy's going towards its infimum, which is what we're interested in. So that's kind of nice that this is happening. It's saying, hey, the more points you got, the better off you are getting closer to what those things are. Is that okay? Okay, so I said in the notes how to do this, and when I said what I just said, I'm going to ask you to do this part. So let's review how to do this part. So, how do you do this part? We will show. We did this. We will show. This part. That's what we're going to show. The other part we're going to leave to you, and so because I know that's going to be a homework problem, let's look at this again all together. Okay. All right, so the argument's kind of breaking it up into cases and something. I mean, you could do this by proof by induction. You could do this by proof by induction, but I'm not going to do it so formally. What I'm going to do is I'm going to say, okay, well, let P be a partition. That's P. Partition of A to B. Okay? Okay. So this is kind of like case one. Suppose, I'm going to break it back up for a second. Suppose P star is a refinement of P. Hey, Angie, what's it mean to be refined?
It means it like has more points.
Right, it's got the same points P does
With extra.
with extras. That's a good generic way of saying it. That's the definition, subset. Okay? Okay. I'm so non-musically inclined. Not that this has to do, where's this coming from? I'm so non-musically inclined. So where I'm going to see this person I haven't seen in a long time, it's at the Methodist church where she attends. I'm going to go to church. I go to church. And so I told her, I said, look, I'll open up the hymn and I'll hum. But there won't be any really singing. I've gone to a Methodist church every once in a while. I'm not Methodist, but I'm not a singer. Why is this bringing up? I like music. I enjoy music very much. Can I play an instrument? Yeah. I took an exam when I was in 6th grade to talk about our music abilities, what we might be suited for the band. When I was in 6th grade, everybody knew I didn't want to be in the band. I like playing. Okay? I wanted to go to physical education. That's what I wanted to do. But they said, well, you take this exam. All we all had headphones on. What's this going to sound like? I remember taking it. And they came to me afterwards and said, John, did you intentionally try to do this badly? That's what they said. I'm not kidding. This is not a made-up story. This is not a made-up story. That was actually, do they still give this exam? Does anybody know what I'm talking about? No. Does anybody know what I'm talking about? I took this. I took this. And that's what was said to me. I remember I was sitting next to Glenn Little was his name. And I kept on thinking, hey, Glenn, what are you doing? You're marking down all the wrong answers. I mean, it was nothing, it was graded on. I was like, what are you doing? I was trying my best, but that's not what I heard, okay? What we're supposed to be there. So I'm thinking of a Beatles song, to every time, turn, turn, turn. You know what I'm talking about? Every season. You know what I'm talking about? Yeah, that's what I'm sitting here thinking. That's why I'm remembering to turn this thing. I'm thinking of the Beatles. That's what I'm doing. If they could make a roller coaster that followed my train of thought, oh my goodness, all right, where are we? We're here. We're talking about this refinement. We're in this proof, okay? That was your break. That was your break. Okay, so we got to refine. so here's case one. That's what I had started to write earlier. So here's case one. Look, it just, as Angie says, it's got more points. Well, the first case maybe just got one more point. Is that okay? That's kind of case one. Script P star has one more point. Than script P. Okay, so it's got one more point. Well, that new point, let's call it something. X star. Yeah, that's what we call it, because it's in prefixed star. Okay. Well, it's still in A to B, this X star is. And it's a new point that wasn't in P. P's got a bunch of partition points, splitting up A to B. This X star is in A to B. So it's got to be between, X star's got to be between two partition points of P. Is that okay? That's what we say. Well, it's got to be in A to B. Say, we have X, I don't know, we'll give it a name. I'll give it the name that I gave it in we'll call it X sub I. Minus 1. Say X sub I minus 1 is less than or equal to, well, it's not less than or equal to, it's got to be less than. X star is less than X sub I. Okay? Where X sub I minus 1 and X sub I are elements of script P. So, here, what we do next is we'll let, the picture is, everybody, you know, here's A to B. Here's what we're thinking. They got a lot of partition points in script P, but the only two that I'm really worried about is this one. Here's X sub I, that's X sub I minus 1, here's X sub I. And somewhere in between there is X star. That's right. There you go. That's good. Okay? That's what we're looking at. Now, here's what I'm thinking. When I talk about these lower sums, you know, for P, I'm looking for the lower sums. It's a sum. It's a sum. I run from 1 to n. What is it? It's the little values, the m sub i's, little m sub i's, times the alpha x sub I minus alpha x sub I minus 1. Is that okay? And so you're talking about the smallest value of f over this region. But when you're looking for P star, you're talking about the smallest value of f over this region and that region. And so what I'm going to do is I'm going to let w sub 1 equal to the infimum of all x's in between x sub I, and you know, x sub I to x star, infimum of f of x. And let w sub 2 equal to the infimum of all x's over, let's say, x star up to x sub I of f. This is wrong here. That's where you point, and that's right. Good, good. That's what we want to hear. I want to take one more second. I said something about the roll. 2 people told me they weren't coming. And if everybody's here, that means I don't have to do the other session. So I'll make sure. Tiffany, you're here. Christy's here. Ashley's here. Allie's here. Melissa's here. Angie's here. Julie's here. Aaron is here. Matt is here. Jennifer's here, Joanna's here, Dennis is here. If you gentlemen would like to see me for what I did right before we came in, we can do this. Okay, all right, I'm going
You're going home.
home. I want to, I meant to say this last time. Ashley, so please forgive me for mentioning you, but I don't think it's nothing bad. Is that one of the reasons we were having 2 sessions is possibly somebody would need it. Ashley said, I might need it. And last time when you came, that meant I didn't have to do it. So I was grateful. Not that you had to come, or did it? We were going to do 2 sessions, but it made it easier for me. So I hope it's not too hard for you. And you, we're going to do 2 sessions every time. But if you can make it, great. It helps me. If you can't, we're not worried about it. There's no problem. I'll get better at explaining it the second time. So that would be benefit for me, okay? So I'm mad at you. Why are you here? I would have gotten better at doing this. See if you didn't come. I'm mad. That's what we're going to look at. All right, so here's where we are. And what
Next week, or next time, we will have to have 2.
Next time we'll have the test.
I know.
Okay. Okay.
Test will get easier the second
Look, that sounded so bad. Okay, so here's what we're saying. We know, let's look at this. Let's compare, what is the smallest guy over this region? Have I turned? No. What's the smallest guy over this region for the alpha values called? Notationally, what's it called?
Alpha and beta.
Yeah, but what symbol do we use in the
Yeah.
lower school?
Oh, yeah. Middle
M survivor.
All right, that's what it is. Little M survivor. That's what we're looking at. All right, let's compare this guy. Look, if you take, I feel like Jeff Potts with me. If you take the smallest value of this whole region, okay, the smallest value of the whole region, and just compare it to the smallest value over this region, which one's smaller? Is it the one over the bigger region or the one over the smaller one? Which one's smaller? No, not necessarily.
One in the smaller.
It's the one over the bigger. We're saying you're the smallest thing over this region. So over this region, the smallest ones are the same, but it might have got smaller. Is that okay?
I still got
I thought our function was increasing.
No, that's the alpha.
These are.
But the little you did fine, Matt. That's a good question. The alpha is increasing. We're not talking about the smallest values for the alpha. We're talking about the smallest values for the F. Is that okay? It's not alpha. We're talking about F. The M sub i's are for the F's. Is that okay? They're the enthemums. I've erased it. Remember this. The M sub i's
For the X of X.
is equal to the enthemum over all the X's in the right region, okay? Of the F of X. That's what it is. Not the alphas, okay? That's a good thing to ask, okay? Good thing to get ourselves straightened up with.
I'm so confused. But what if it's a decreasing, what if f of x is decreasing? Wouldn't the smaller come from the second interval?
It could be the.
The smallest one, the smallest value over here,
Yeah.
M sub I, shortest person in the ring.
Yeah, okay.
Compare it to the smallest person from here over. Which one's got to be the smallest?
the smallest one in the room.
Is that okay? That's what we're comparing. Is that all right? Okay, so here. No, now that better be what's in my notes. So which one's bigger is W sub 1 is bigger than M sub I. Is that okay? And W sub 2 is bigger than or equal to M sub I. That's what it is. The smallest one is over the whole region. Okay? The smallest side is over the whole region. Definitely will be smaller than the ones, smaller than or equal to the ones that are just part of the region. Okay, that's what we got. Okay. All right, now, let's look at this. We say, look at the lower sum with the refinement minus the lower sum with the regular partition. I didn't write all those out initially on the problem. But you know what this is? This is I've moved. I'm glad. We're going to move back. Okay. So look, when I look at these lower sums with the refinement and minus the lower sum with the regular partition, everything's the same. Everything's exactly, the sums are exactly the same, except over one interval in P. It's the one between x sub I and, x sub I minus 1 and x sub I. Is that okay? So the sums, for the lower sum, they're the same. They include the same things in both parts over here. Both of them, because they're exactly the same things. Except here's the only difference. Is that okay with everybody? Okay, so I'm going to print this thing. Okay. So this is equal to the sum, and here this would be, this part is W sub 1 times alpha x sub I minus 1 minus alpha of x sub I. Okay? Plus, what else is different here? W sub 2 times alpha, this wouldn't, x sub I. I made a mistake. What should it have been? X star. That's right. That's what it should be. W sub 2 times alpha. I didn't write this down right either. This is wrong. Correct me. Can anybody correct me? This is wrong.
Should be switched.
All right. You said the right thing. That's good.
Because it was bigger.
Yes. And then here it's going to be alpha x sub I minus, come on somebody. That's right. Good, good. I'm glad. That's where we're going. That's the part that we're going to have over this region for P star. Is that okay?
Why is it a plus in the middle?
Why is it plus? Because, great, Angie, we're talking about the whole thing. The lower sum right here is a sum itself. It's a sum. And so it's got a bunch of terms. These are two terms in that sum that are different than the two terms in that sum. Is that okay?
Yep.
Okay.
That's the missing, that's the extra piece in the middle.
Yes, ma'am. Minus, so it's minus because this. But there's only one term in that P. Okay, that corresponds to the two terms here. And what guy is that in the lower sum of P? It is the m sub I times alpha, it would be x sub I minus alpha x sub
I minus 1.
I minus 1. That's right. That's right. Now I'm going to multiply it out. Okay, so I get that. So that's what we do. We multiply it out. W sub 1 times alpha x star minus W sub 1 alpha xi minus 1 plus W sub 2 alpha x sub I minus W sub 2 alpha x star. And then I'm going to write it right here. Minus, this should be brackets here. It's m sub I alpha x sub I. And then minus and minus makes a plus, so this is plus m sub I alpha x sub I minus 1. Okay, that's what I got. And then what we do is we add and subtract the same thing. And we're going to add and kind of rearrange some terms. So I'm going to write down what is advantageous for us here. Remember what my whole goal was to show in this case, we're going to slow down this. To show in this case that this guy is bigger than that guy. That means this subtraction better be a positive number. That's the goal. Is that all right? I'm going to show this guy's positive. So I'm going to show this guy's positive. So I'm going to add and subtract the same thing. So here I'm going to rearrange the terms. Okay. So here's what I'm going to say. I'm going to say this same thing. So the W1 alpha x sub star, I just write that down. Okay, here's what I'm adding to. Minus m sub I alpha x star. Okay, that's new. You guys hear me? That wasn't there before. I'm adding it. And I'm subtracting it at this point, so I better add it later. Okay, so I got that. And so then this guy's already there. W1, you check it out. Next term. W1 times alpha of x sub I minus 1. Okay? Plus, I might rearrange some terms here, but here's m sub I alpha x
Star.
I'm going to just leave it as x sub I minus 1. Okay, this is I. Okay, so let's find that term. Where is it? Which one did I just write down?
Very last one.
Okay, I'll pick this one. Okay? That's that guy. So there's the x stars together. There's the x sub I minus 1s together. Okay. Then I'm going to have W2 alpha x sub I minus m sub I times alpha x sub I. Let's check that out now.
What's the symbol after?
It's plus.
What should be plus?
At the end of your line.
Of the top line.
Or no, it's.
Right here.
Top line.
End of that.
All right.
Okay. Let me have Nate. Can you help me? Which way I'll go?
Right,
Nate?
all the way to the end.
Yeah, all the, one more, what goes between that and then start.
What symbol? Okay. So W2 should be plus. Thank you very much. Thank you. So I want to make sure I'm writing down the right thing. So where's this minus m sub I alpha? It's this guy. It's this guy. So I'm writing it down from this few pages, but I just want to make sure I'm making mistakes. Minus, here's W sub 2 alpha x star. It's this guy. Okay. And then plus
This is your.
m sub I alpha x star. So I'm adding this guy to compensate for the subtraction earlier. We're not doing anything magical. Okay. I added and subtracted the same thing. Okay. Now we're not going to do something magical either. What we're going to do is we're going to factor by grouping. Okay. And so really we're going to think, okay, these are two terms. These are two terms. Is that okay with everybody?
Yes.
We can factor out from here. What we factor out is yes, an alpha x star, and this is W sub 1 minus m sub I. Here this is minus, which is going to change. I pull out the alpha x sub I minus 1, pulling that out. That would make this a plus W sub 1, and this is a minus m sub I. That's what it would be. Okay? So that's those two terms. And then here I can take out an alpha x sub I, and this is W sub 2 minus m sub I. And then here's minus, I'm going to pull out alpha x star, and we're left with, this will be W2 minus m sub I. And then out of those, I didn't put that step in before on the proof, okay? So I'm factoring by grouping. And now I'm going to look at that top line and say, hey, I can pull out a W sub 1 minus m sub I times alpha x sub star minus alpha x sub I minus 1. And then plus, here I pull out the W2 minus m sub I. And here, this is an alpha xi minus alpha x star. Am I anywhere? I'm nowhere. Okay, so we did all this work. I'm sorry that I didn't turn it, but we did factoring by grouping. We subtracted and added the same thing, rearranged the terms, factored by grouping, and no, I'm done at this point of looking at it, I believe. Okay? So let us remember some stuff here. In our partition, I got some room right here. So this is x sub I minus 1. Here's the x star. And this was the x sub I. Okay, so I want to look at that. What do we know about alpha this time now? It's increasing. I'm going to stop. Let's give everybody a second. Breathe.
All numbers.
Yeah. So we give everybody a second, okay?
Thank you.
Yes, sir. That's right. I mean, that's fine. I mean, what are we supposed to do?
Work somebody like that? I'm not for that.
It's not fast enough.
No, sir. You're fast enough. You know, it takes time. You know, that's one of the things I feel strongly about myself. I don't mind being asked to work. I just have to be given the time to do it. Okay? That's what I think. I don't mind being asked to do stuff. Just Just give me time to do it. Alabama didn't play this weekend, that's right. Last weekend, people told me, said, you know, John, Alabama really had struggles with I saw scores 21-21. I said, did you see the game? I don't know if Alabama's going to lose, next game or all the rest of their game. I don't know. They had 600 and something yards against Florida. It wasn't, Alabama just made a few, that game the score didn't indicate what was going on. Alabama was killing them. If I were a Florida fan, I'd be sitting there thinking, what is going on? We can't move the ball. They're moving the ball all the time. Something is very wrong. That's what I'd be thinking. For me, I was thinking, why aren't we beating them by 70? That's what I was thinking. Because that's what the score looked like. That's what the play looked like. It's not that they're going to do that every game. But we play like that every game, people won't have trouble beating us. As long as we don't turn the ball over. All right, so look, Aaron said these things were positive. Let's figure it out. Here's the reason this guy's positive. It's because W1 is bigger than M sub I. So you take bigger minus smaller, definitely greater than or equal to 0.
Yes.
All right, now look, I was talking about X sub I in comparison right here of X sub I minus 1. Which one's bigger? Not X sub I, X star. Which one's bigger, X star or X sub I minus 1? X star. Alpha's increasing. So alpha of X star is bigger than?
Alpha of X minus
Okay, so this is definitely greater than or equal to 0. So this part's greater than or equal to 0. Same thing for this being positive, same thing for this being positive. Is that okay? So this is greater than or equal to 0. And so what that means somewhere. Yeah, that's good. I'm grateful. Yeah. I could be a director. So what that means in this case that meant that this lower one here was less than or equal to with the refinement. The lower one with the refinement. That's what we have. Okay, that's in this case. Case 2, if P star has K more points than P, we just repeat the same argument K times. Thank you. So that's what we do. The difference between, if we had those partitions again, the lower partition, when we only had one difference between the points, we were just looking here from A to B, and it was just over this little region we were looking at the difference, okay? Does that make sense to everybody? If we got K differences, we're going to have K little spots. And we just isolate on each one of those spots and do the exact same thing we talked about. Is that okay? That's what happens. Okay. All right, so that's the proof. And the upper one are going to work analogously. Okay? That's what we're going to do. And that's what you're asked to do eventually. All right. Well, with that being the case, what I want to talk about next is another fact, and that is this is a very interesting fact. Let me talk about it. It's always true that this is very, very interesting. A theorem. that the lower Riemann-Stieltjes integral, which we know exists, is always less than or equal to the upper Riemann-Stieltjes integral. So, Melissa, Dennis, Christy, you know, if you ever wanted to show two things were the same, one way of doing that is showing, you want to show A and B. I'm talking about two things, A and B, not what's written up here. You want to show A and B are the same. One way of doing that is showing that A is greater than or equal to B, and B is greater than or equal to A. And so half of that we're going to get right here all the time. So maybe there could be arguments for showing when they're the same, and when we have something for free, we get this every time. Does that make sense? So that'd be kind of nice if this were true, and it is true. And this proof is easy. It's easy. So here's what happens. Let me show it to you. It's very easy to prove. We let P star be a common refinement. Be the common refinement. Between partitions to arbitrary partitions. Between two, arbitrary partitions. They're given to you. Script P1 and P2. Okay. Then by the previous fact, here's what we have. By the previous thing we just did. Here's what we have. The lower with P1, F, and alpha is definitely less than or equal to the lower with the refinement. And that's definitely less than or equal to the upper with that refinement. And that's less than or equal to, that's what you guys are supposed to show, the upper with P2. Okay, that's what we got. So that's one thing we have. And so here's what we have. So this is very nice. I mean, this is amazing what I'm about to write down. Right here, this is just amazing. By the thing what I just did, what we can say, well, the conclusion from this is, I mean, it's amazing. What that says is, the lower of P1 F alpha is less than or equal to the upper of P2 F alpha. Look, P1 and P2 were arbitrary. What we're saying is every lower sum is less than or equal to every upper sum. Is that okay? Not just when you have the same partitions involved. When you have the same partitions involved, that's easy. Okay, to show that the lower is less than or equal to the upper. We're saying it for every one of the partitions you could possibly take. It's pretty amazing.
Now, is that because, I'm still trying to get these definitions in my head, is that because alpha in this particular kinship is increased?
That plays a factor in it. Yes, sir. It sure does. Because it played a factor about getting this. It played a factor in getting this, man. And, man, I'm going to tell you something. There's no prefacing needed. It takes time to get, you don't have to say, well, I'm trying to get, it's tough. It's hard, okay? We all, nobody gets this immediately. Okay? Well, I didn't get it immediately. How about that? You know, I mean, anybody, maybe there are people getting it immediately. It's not me. So, look, we got this result. And we also, this result comes from the partitions being the same. See? And this result is something I'm asking you to do. So really, it's just because we can write down this statement from it, and we just look at it and say, hey, we're saying no matter what P1 is, and no matter what P2 is, we got this relationship. So it works for all P1 and P2. Okay? For all of them.
And you said every partition includes the lower point and the upper point.
Yes, ma'am. Sure does. No,
And
it's,
the P star is a common refinement between the two of them.
Yes, it is. So it's a refinement in particular. So that's when we get to apply the previous fact, because the previous fact just had to do with refinements. Didn't have to be the common, just any refinement. So that's what
Remind me again what common refinement is.
it's where you union up the two partitions. Okay, so look, here's what we could all this so we want to look, what am I talking about for the lower sum? What's the lower sum? The lower sum, I'm sorry, lower sum. What are we talking about when we talk about the lower integral? We're talking about the supremum. We're talking about the supremum of this thing. Here's what I see. This guy right here is going to be an upper bound for all of these guys. Not just for P1, but for any. P1 was arbitrary. Is that okay? So if you say this guy is bigger than or equal to every one of these lower, that means if you look at the supremums, the supremum of that set has to be less than or equal to, because it's the least upper bound, than any other upper bound. And what I'm telling you, by looking at what's being told to us right here, is this guy right here is an upper bound for this set over all partitions. Is that okay? So that means that the supremum piece of 1F, well, I would say it's the supremum of the lowers. This is over script P. P1F alpha is going to be less than or equal to this guy. And that says, so the supremum of all these is that lower Riemann-Stieltjes integral. Now we stop for a second and say, well, wait a minute, P2 was arbitrary. Well, so this is a number. It exists. And we're saying, no matter what partition you have here, this upper sum is going to be bigger than this number over here then is a lower bound for the set of all these upper sums. Is that okay? And if you look at the greatest lower bound, or the infimum, it's got to be that number. Is that okay? That's what happens. And the infimum, I guess I should say, infimum of this, let me do a little slower. I didn't write my last name. Well, where's upper? There it is. This infimum is all over all partitions here. And so this quantity, this is less than or equal to, okay? It's not a subset. If I make a mistake, Franco, please let me know. That's that proof.
Is that a P or P2?
I've changed it to P here.
Tell me why.
Should you have done that also in this?
Yeah. Didn't do the Suprema.
Oh, no, yes I did. Yes I did.
Thank you very much. That's why I could understand.
Yes ma'am, that's
Could
correct.
you
You're
explain to
correct.
me again why is P and not P2 then?
Yes ma'am, yes ma'am. So here, we're saying that P2 was arbitrary. So no matter what partition we're taking, we're just saying we're taking any partition. This holds true. So if it's true for P2 and it's arbitrary, it's true for all the partitions. Is that okay? And so that means that this is a lower bound for the set of all partitions, the set of all upper sums. Yeah, I think that takes a little movement. I mean, it's not just automatic. It'll be clear. That's what it's about. That's amazing. Okay, so we have that. And then this is, at least I'm going to write this down. But I will wait to make sure we're all okay. So if you guys got questions, you ask. Okay. Does anybody have anything they want to ask about? Well, this, I know, we're getting close to it. We all see. Let's get time. we're anxious to quit, I know. But also we're anxious to make sure that we ask the questions we want to. Here's the big theorem. This is the big theorem in terms of just establishing the Riemann-Stieltjes integral existing. Here's the way to establish it for particular functions. It says let F, it says F is Riemann-Stieltjes integral on A to B. If and only if, for every epsilon greater than 0, there exists a partition such that the upper sum with this partition, so that is a particular partition, minus the lower sum is less than epsilon. The proof I did in class. The proof we did in the lectures. Okay? I can do the proof now, no problem. Or we can say, hey, let's call it quits, it's in the lecture, whatever you want to do. But before we call it quits, no matter what, I want to make comments. What this theorem is a way of establishing that a function is Riemann-Stieltjes integral. And it's also, if the statement applies for Riemann-Stieltjes integrability, it also applies to Riemann integrability, okay? So this is a way of saying it's Riemann integral. Can we say what the integral is? No. We're just saying it exists. It's some number. I don't know what it is, but it's out there. Does that make sense? And for some functions, it's not out there. Okay? For some functions, they aren't Riemann integral. We'll get to that a little later. We haven't got it in the notes yet. But there are some that aren't. Do we want me to do the proof? It's okay. This one doesn't take long. It's okay to say, no, it's in the notes. If it's no, if you have questions about it, you can ask me, okay? I'll just call it quits there. Is that all right? Okay, so I'll be sending out via email, I should say, a study guide that I gave last year over chapters 5 and 6 for the test, okay? If we get through all that material, that's great. If not, I'm going to tell you where to cut off. But I'm going to give you that Monday, so you can start seeing what I had asked about before, okay? And then sometime in the near future, I'm going to give you a homework assignment, and you'll be over chapter 6. Okay? Is that okay with everybody?
This will probably do with the midterm, the day of the midterm.
I can do that, but I was thinking that maybe I'd get it done earlier. I asked you to, so I could grade it and get it back to you. I don't know what's best, but I think that's best. Okay. All right, well, that having been said, I'm done, and I thank you very much for coming. Thank you. Yes, sir.
I have a question.
I'm ready. Come on with it now.
Now,
Actually, well,
this is a general answer.
school started and like.
General partition. Yes, sir.
Scattered through. So I have 2 red ones, and I have red.
Red one's green.
Visualize the function.
The only reason I think
So this,
like you're stuck.
this has error in it, but this is the actual lower.
This is a number. I can tell you this is a number. That's the way.
You just said they were like,
And I wouldn't say that this is actually, this is just a number. And what I'd say, this is this is a true statement no matter what the partition is. No matter what. And you think of this as a function. This is something that gives out numbers. This number is less than or equal to every output function. What is our function acting on? Let's just say p. So no matter what p is change, this will be true. This is a true statement. So if you say, well, take the infinity number, it's the smallest of all. Well, it's definitely going to be bigger than this because the infinity number. First of all, this is a lower bound for it, and the infinity is the greatest. When you drew your picture here, what you're doing was you're saying about alpha increasing, but F might not be this. Alpha's increasing, but F might be doing that.
So I guess, so trying to incorporate what you just said, if I think of U, this is a function of
Just say P.
P.
Yeah, because these guys are gonna be fixed in this case.
So this is a numerical value
Because
that
he's
is
got
below all the values in that curve that you just drawn.
If this curve represents that function, that function, not F, not alpha, but that function. Yes, sir. Yes, sir.
We just have, this is a constant here, and then this function, whatever you have, represents, and because it's from A to B, this represents all the possibilities.
I wouldn't say from A to B, it's over partition.
Okay.
Then what you're thinking is right.
Okay.
So this picture represents this function, okay? Not F, not alpha.
So it's just over the partition that we're thinking about. Okay. That's a little better.
That's what I was doing. I'm being serious. I was watching videos. I'm being serious. I was watching
Okay,
videos.
that does make a little bit more sense. If I think of it as a function.
No, it's really not.
Okay,
You wanna stop there?
okay.
Dr. Whitaker, I have a question. I